means I got to end this class. I got to be out of here by 12. All right. So the reason I'm telling you guys all that is, number one, it means obviously we'll be done by 12. But I want to kind of get an idea of how many folks. I know there's going to be a handful of folks that want to speak with me afterwards about midterm. Can I just get a little wave if you're looking forward to speaking with me after midterm, or after we're done here? A few. Okay, good. All right. The only reason I'm bringing that up, folks, is just simply because that's telling me how far I should go this morning. So here's the play. We're going to finish off chapter 6. We're going to be done with chapter 6 when we get together again on Thursday. We will get into 3D stacks. We'll spend Thursday doing that. We'll spend Monday of the 11th week doing that as well. And gosh, probably by Thursday, I better be doing something with you guys as far as final exam goes. So I got to think through that one. I don't have answers for you on that one right now, but we'll be ready to discuss that on Thursday. All right. Any questions about anything we've been doing so far, folks, before we get started and finishing off our conversation on friction? We all saw, when we got together on Thursday, we all saw, at least what I hope we saw, a takeaway where we understood how to represent frictional forces on a three-body diagram. By the time we got that done, by the time we saw how to represent those frictional forces, after that we saw absolutely nothing new. We saw still just a three-body diagram and the applications of the equations of equilibrium, and just like everything else we've done so far in the course, it all just ended up solving the problem. The big takeaway at that point was, again, that there is so little new happening right here, right now. As we've moved into chapter 6, for example, all we needed to understand was how do we show those frictional forces. And probably two really important things that fall out of that. Number one being that frictional forces are actually not adding an unknown to our problem. They're actually adding a proportionality relationship to the normal forces that are already there. In other words, that's a very indirect way of simply saying a takeaway we've seen so far is that frictional force is nothing more than the coefficient of friction, the proportionality constant, multiplied by the normal force. So we're not adding anything new. The second, and I think the by far most important takeaway, and I mean this is the thing that we just need to make sure, if we get this part down here and really buy into this, then friction's an absolute nothing burger, and that is that the directionality of the frictional forces must always oppose impending motion. If you do that, and you do that part right, the rest of this is pretty straightforward. Check out the problem I put up on the board right here. This is a problem that actually there's an equivalent of this one that goes way back into chapter 3, and I don't believe we looked at this problem back then, but sometimes I do, and then I come back to this. If we did, fine. You've seen this before. If we didn't, kind of new to you here. So check out the narrative on this one. Well, before we even get there, let's look at this. We've got an inclined surface right here with a 100-pound crate or box or something there. And really importantly in this problem, and the reason I, again, say that sometimes I've already visited this problem earlier in the course, is that there's a really important element of statics in which we look at belts. Belts, pulleys, like chains, blocks and tackles, stuff like that. We need to see this before we get out of statics, so if we haven't discussed it already, we're seeing it right now. What we got here is this 100-pound block of something or another on an inclined surface right here. We've got a pulley on the front of that, and then a series of pulleys that you see right here with this one long, large belt that wraps around. So the belt is anchored here. The belt, the blue line, I probably should have drew it in some different color, but I didn't, goes around this pulley right here, then it comes around this big pulley, around this big pulley, all the way down to this small pulley down here, around this pulley, and it comes back and it anchors right there. All of that is holding up some kind of a weight right here that we're representing with the nomenclature W sub B, or let's call it W if we want to. We'll come back to fix that if we choose to do so. Having said all that, listen carefully to the narrative on this problem. It reads this: if the coefficient of static friction between block A and the incline is mu sub s equals 0.3, let's just stop right there. They have told us that we've got a coefficient of friction going on between block A and the incline right here. It tells us it's a friction problem, obviously, but it's giving us a value. We're being told that mu sub s is equal to 0.3. So with that knowledge, you might as well just write it down. Now go back. So if the coefficient of static friction between block A and the incline is, again, 0.3, determine, hear this now, determine the range of cylinder weights, over here W sub B, for which the system will remain in equilibrium. And we're told to neglect all pulley friction. We're told to neglect all pulley frictions. Let's make sure we understand what that means. What the neglect all pulley friction is saying is that the problem is saying to us, this is like the good old days in which everything is smooth except for the surface between the block here, block A, and the inclined surface. That's the only place we have friction. Everywhere else, no friction. All right? So everywhere else is smooth. But then we get into this weird thing, this weird, like, again, range of cylinder weights for which the system will remain in equilibrium. So we have to ask ourselves, what exactly does that mean? And the answer is this. Equilibrium for this system right here means that the box is sitting, is static. In other words, the box is sitting here. It's not sliding down the plane. If it was sliding down the plane, it'd be out of equilibrium. And at the same time, there's not so much weight hanging over here, because let's face it, if we put a really large, some sort of a large amount of weight over here, then that would be enough weight to pull the belts and pulleys down, which would cause the box to go up the plane. So we're being asked to figure out what's the range. The range being how much weight could we hang here, or how much weight, I should say, would we need to hang here to prevent the box from sliding down the incline, and what would be the maximum we could put here to prevent it from going up the incline. And even before we attack the problem, in what I just said right there, we see the solution. The solution, which we just talked about a moment ago, hinges on two very important fundamentals. One being we know how to represent frictional forces, we'll do that in a second, but the other being that friction must oppose impending motion. In one case, the impending motion is going to be that the box, this thing here, is going to go that way. But in the other case, the impending motion has it going that way. We're going to work this problem twice, and we're going to change the directionality of our friction force to see what the range is going to be. So to do this, let's take this problem on. And importantly, folks, even though there's a lot more busyness going on here in this problem, this goes back to, again, just the fundamentals that we've been talking about since day number one. That being that we look for things to make free body diagrams out of. We apply forces, we apply equations of equilibrium. If it produces fruit, fine. If it doesn't, we do something else. Nothing's new here, right? So in this case, I look at this and I think, all right, well, what are my options here? The most obvious option goes back to the fundamentals we've talked about before, and that is ultimately we have to have a free body diagram of something that has applied forces on it, something that has the forces that we're looking for. In our case, we're looking for the frictional forces, right? Ultimately, though, we're looking also for the force of this associated with this weight over here. So it's kind of a, hey, do we do a free body of this, or do we do a free body of this? Which one's it going to be? The answer's going to turn out both, but let me start with the box. And you'll see why I'm starting with the box in just a second. So I'm going to do a free body diagram of that box. It looks something like it is. In other words, it looks like the box. So we know that this box here has a weight of 100 pounds. We also know that even though we weren't told this, we don't know anything about its dimensions, so we're going to have to assume it's a uniform crate. So uniform rectangle, therefore the weight has got to pass through the centroid of this. Centroid in this case would be in the geometric center of the box. Now, this is the problem I've told you before, and I would be thrilled to think that as I'm about to tell you all this, you are already saying this would not happen to me. You're probably right, it would not. The error I'm about to tell you about probably would not happen to you, but historically speaking, when I put something like this on a final exam, by the way, would I put something like this on a final exam? Yeah, why not? Historically, when I put something like this on a final exam, 10 to 15% of people will make the following mistake. The weight is 100 pounds. The mistake that gets made, which should never get made, is we look at that and we think, well, it's 100 pounds and it's sliding down the incline, so the weight should be pointing down the incline, right? Wrong. Because weights always point where? Straight towards the center of the earth. Believe it or not, that mistake happens about 10 to 15% of the time. So don't let it happen to you. Let's just put the weight exactly as it should be, right down through the middle of the centroid, pointing straight to the center of the earth, and we know that this is 100 pounds. Okay, done, got that part. Now, as far as the forces, now if you think about this again, folks, we know we're going to create forces, A, where we used to be in contact with something, all right? But B, also if there are any applied forces, we need to show those. There aren't really any applied forces here other than the weight. So let's talk about the point of contact. So here we have a plane of contact here along this 25-degree angle off of horizontal. We got a plane of contact right here. If we think about this as anything else, if we imagine trying to move this box through this plane of contact, would it face resistance to motion? And by now everybody's like, yep, absolutely right. So therefore, sure, we've got to have a normal force here. Let's represent that normal force right here, like so. Let's call it normal force. Now, in this particular problem, we're told that there is friction, right? So if we know there's friction, that the frictional force has got to be shown then along the plane of contact. At this point, though, we've got to make a decision. Do we want to go for the low end of the range first, or we're going to go for the high end? Because remember, if we go for the low end, of the range of weights here, then the box would be sliding down the hill, right? Going down the incline. If we have too little weight here, it's just going to be free to slide down the incline. So the impending motion in that scenario would be going towards the left or lower left as I'm pointing here. And if motion's going that way, then we got to show frictional force opposing it. So the correct direction for the arrowhead, at least for the first pass through, is going to be this way. And remember, the frictional force here is nothing but the coefficient of static friction times the normal force. So 0.3 times n. And then we've got to think about the force that is associated with this pulley right here. Right now, this force associated with this pulley, if we think about the directionality of the pulleys right here, I'm going to ask you to take a little bit of a leap of faith right here, and we can resolve this if we need to through another free body diagram. But whatever these forces are right here, it's going to be represented, or could be represented, as a single force pointing away from this plane of contact right here. And if you're not sure of that, just imagine in your minds doing a free body diagram of the pulley. You'd have the force in this cable, and you'd have the force here pointing back at that. So that reactionary force has got to be a single force going up that way. So let me put that force into my free body diagram, and let me not put a name on it just yet, because there's something I want to show you before we go any further with this, and that is, all throughout the course, we have talked about the idea that, as we all know, when we do a free body diagram, we've got to put a coordinate axis system on the free body diagram, and almost every time we've seen it so far, it's been perfectly fine. Just think of the coordinate axis system as just the usual X, Y coordinate axis system. But I've also said that we will see times where strategically rotating the coordinate axis system can make our math easier. Folks, I want you to look at this. Notice how I've got a force here pointing in that direction, another force pointing in the same direction, and I got a force here that's normal to that. I got three of my forces that are following a directionality that would make it seem logical to include an X and Y axis system that looks like this, which in doing that, I just made this force here and this force here purely X directional. I just made this force here purely Y directional, which means my math is going to be easier to deal with these forces. The only force I've got in my entire system that is not falling right on the X or Y axis is going to be this force right here. And we're going to be able to deal with that because look, If this is a 25-degree incline right here, then this angle here, with respect to my y-axis that I'm about to draw in right here, this angle has got to also be 25 degrees. So, okay, let's roll with that. Now, we still haven't come to the, well, what's this force here going to be? And here's where, again, we're going to have to do another free body diagram. So, in this case here, we go back to the idea that we've talked about so many times now throughout the course, that there's nothing we can't choose to make a free body diagram of. When we did trusses, we saw that we could even take a saw, mentally doing it, right? Take a saw and cut a chunk of our truss out and do a free body diagram of a chunk of our truss that we cut out. Why? Because we can do a free body diagram of whatever the heck we want to, right? In this case here, I want you to imagine, what if we cut these cables right here? What if we cut those cables and did a free body diagram of this weight? So let's just imagine what that looks like. So a little bit cleaner picture here. So I got this weight here, I'm going to call it W sub B. And I've got this thing coming up off of it, and associated with that, I've got this pulley system right here, this pulley I should say, right there. And as you can tell, boy, the artwork on getting these pulleys right is a little bit harder than it might seem. Let's try to make that just a touch better looking, maybe like that. And now, off of that, I've got these 3 pieces of cable that I want to draw here. So I've got this one cable that I've cut. I got another cable coming up off this piece right here. I got another cable over here that I've also cut. I'll put a little bit of an angle onto that one right here. So here are my cables, all right? So what I want you to see here, what I want you to imagine is, again, nothing new, right? What have we done? We've took our original drawing, and we literally took a piece out of that. We cut away a piece of our original drawing that includes nothing but the original weight, the weight of the container. This thing here that's identified as B is still B here, nothing new there. And we've got the pulley, and we've got these 3 cables hanging up off the pulley, or showing drawn away from the pulley, right? So now if you think about this, I want to do a free body diagram. I want to complete the free body diagram of this. All I've done so far is I've made my sketch. But now I need to apply my forces. So I've got the weight of the object here, which I'm going to show as a single force going down. So W sub B is that single force going down. Again, weight's always just pointing towards the center of the earth. And then I also know that when I have non-rigid tension members, i.e. cables, i.e. chains, belts, whatever, rope, you name it, that these can only have tension forces. So I got a tension force here where I used to be in contact with something. I have another tension force over here where I used to be in contact with something. And I've got a tension force right here where I used to be in contact with something. Right? So I've got this tension force here, this tension force right here. Let's see here, folks. I want to back off this for just 2 seconds here. Oh, yeah, right. Tension force here and tension force right here. I had to think about something for a second before I could go on with that. Folks, there is a very important assumption we're making right here. This problem doesn't say a thing about it, but we have to understand something. Even though the original diagram shows that the diameter of this pulley here is apparently smaller than this diameter up here, which causes there to be a slight angle on this cable right here, we have to understand that without any dimensions, we are going to assume that that's negligible, all right? That means that we're going to assume that every one of these tensions are purely y-directional forces. Now that also means that if I sum my forces now in the y direction, I'm going to have 3 times t here is equal to the weight. And this leads to something very, very important. That means the tension in each cable is nothing more than the weight divided by 3. And that leads us to a principle. Now again, as you heard me say at the very beginning of all this, folks, sometimes in the class, sometimes in teaching this class, all the way back to chapter 3, we take a look at a pulley problem, and this is already established. I'm just going through my memory, and I don't remember doing that with you guys, so I think this might be, maybe we're seeing it for the first time. I could be totally wrong, I have no idea. But the important takeaway is this: whenever you're dealing with pulley problems, it turns out that the tension in the cables is always equally distributed. Very important idea. Always equally distributed. So even before we did this free body diagram, if we knew that we had a weight hanging down here of W sub B, before we did that FBD, then if we understand that the cable force must be equally distributed, then we find that if this is WB here, then 1/3 of WB has to exist here, 1/3 of WB has to exist here, and 1/3 of it has to exist over here. So now with that in mind, think about this and just trace this through, folks. If this force in this cable is WB divided by 3, then if this is WB divided by 3 here, then what do we got right here? WB divided by 3. What have I got right there? WB divided by 3. And what have I got right there? WB divided by 3, right? We are distributing the force in the cable equivalently throughout the system. Which means now when we come over here, if you think about what is this force right here, if I've got one force in the cable that's WB over 3 and another force in the cable that's WB over 3, and I add both of those in my x direction, then what I have here is 2 times WB divided by 3. And now with that, and very importantly, I got a fully done free body diagram right here. If you think about the free body diagram that's in front of us right here, we got the sketch, we've got the axis system, we've included all the forces of what we used to be in contact with, the weight, the normal force, the friction force, they're all there. And now we've got nothing left to do in solving at least the first portion of this problem. We have nothing left to do than just the equations of equilibrium. So in following the same old, and remembering the 2, we define our x-axis like this. If I now sum my forces in the x direction, I will have the following. I'm going to have 2 times WB over 3. Plus 0.3 N. This force here is purely y-directional, so we don't have to worry about that. But I have a x component associated with this 100 pounds here, which if you look at it, if positive x is going up the way I'm holding my arm right now, this is tending back towards negative x. It's going to be minus 100 times this little piece here. So it's going to be this little piece right here. So it's going to be minus 100 times the sine of 25. So, wrong place. Minus 100 sine 25. So I've taken care of that one, and this one. That's my equation. And as I look at that, I see, of course, I got 2 unknowns. I can't do anything with that. So let's go ahead now and sum forces in the y direction. And very importantly, we'll note that this force here is purely x directional. This force here is purely x directional. So the only y direction force we have is N, which is drawn in the purely y direction, in the positive purely y direction. So I have N. And then here, I see this force here is tending towards the negative y direction, and that's going to be negative 100 times the, in this case, cosine of 25. So minus 100 cosine 25. And folks, that is the entirety of the y direction equation. So we're going to set that one equal to 0. And it should be quite obvious right now that we can solve that equation. We can solve this second equation here for n. So let's go ahead and do that. We're going to have, in this case, then n is going to be equal then to 100 times the cosine of 25. Noting, of course, that the 100 cosine 25 became positive when I slipped that over the other side of the equal sign. And 100 times cosine 25 ends up being about 90.63 pounds. And now that I know what n is, if I go back up to this equation right here, which by the way, I'm going to label that equation equation 1, so we're going to use it a couple times. If I now substitute that value of n into equation number 1, which I'm going to come way over here, so let's just note this here. From equation 1, if n equals 90.63 pounds, then we're going to find, after solving, plugging that in here, solving for WB, we're going to find that WB ends up being about equal to about 22.6 pounds. So, in the context of solving for this problem, what we just figured out right there, and again, remembering that we were trying to find the low end of the force range, the low end being the amount of force, the amount of weight I'm going to need over there that would be adequate to prevent the box from sliding down the hill. I now know that I need at least 22.6 pounds to keep the box from sliding down the hill. Now, I just need to reverse the frictional direction to solve for the high end. Why? Because remember, nothing is going to change. As far as the free body diagram goes, nothing changes in that this is still the same 100-pound weight. It's still got a normal force, yup. It still has the same force pulling on it at 2 times WB divided by 3. That's the same. The only thing that's going to be different is on the high end, if I get too much weight here, if I put too much weight on this, then the box is going to scoot up the hill, which means the impending motion would be that way, which means for the second part, if my impending motion is going this way, I've got to have my frictional force pointing in the other direction. It's got to oppose motion. So now, for part 2, I'm going to change my arrowhead over here. It's no longer going that way. Now the impending motion of the box is into the upper right. So now I'm going to show my frictional force opposing that. So it now goes this way. And with that said, we should come back over, and let's remember, this particular force right here was a purely x-directional force. The only thing that changes is it used to be going in the positive x direction, but now in part 2, which I'm going to draw this in red, in part 2, this becomes a minus 0.3 n, because now my force is going in the purely negative x direction. So now if I go back and resolve my problem, now if I work a new equation 1, let's just write this out. If I now sum force in the x direction, I'm going to have the following. I'll have 2WB divided by 3 minus 0.3 n. In other words, this just changed here. Minus the same 100 times the sine of 25 is equal to 0. Now, folks, if I solve this thing for, if I plug in n is equal to 90.63 pounds here, and I solve this, I'm going to come over here and do this for part 2. So for part 2, if n is equal to 90.63 pounds, now from equation number 1, we are going to get the high end, WB, ends up being equal to 104.2 pounds. And we just solved the problem. It is worth noting here, folks, absolutely worth noting, that changing this arrowhead right here did not change this equation here at all. Nothing changes on that equation. So we're still going to have the same normal force of 90.63 pounds. The only thing that changed right here is once I figured out what n was and I plug it in right here, this becomes positive on the other side of the equal sign, making for a much bigger term, and we get the much higher WB over there. Problem is solved. Based on what we just determined here, folks, we found that we need at least 22.6 pounds to keep the block from sliding downhill, but if we exceed 104.2, it's going to be pulled up the hill. Our range is 22 to about 104 pounds. Problem solved. Once again, we see that friction, at least from the perspective of the free body diagram just doesn't add anything majorly new to what we've already been doing. We now have a frictional force, but it's a function of some other force we've already got. And you saw in that problem right there, I think that problem better than any problem I've seen in all of chapter 6, I think that problem illustrates most succinctly the importance of being so judicious and analytical about making sure you're drawing your arrow to oppose impending motion. Such an important thing. Does anybody have any questions further on that one right there? Yeah, fire away.
I don't understand where you got the 2/3 WB from.
Say it again for me.
I don't understand where you got the 2/3 WB from.
Sure. Let's run through that again. So it really comes down to, again, the idea that if I've got a single pulley, and it might be a little bit easier to see this. Let me try something here. If I had, let's just say I had anything, some sort of a weight, and I've got a simple pulley here. So let's say that that weight is associated with a simple pulley, and there's a single cord around that simple pulley, right? Let's say that that's the case. In this case here, if you think about the weight force that's being applied to this here, and the continuity of the cable, if we took little free body diagrams of the cable, whatever force is going this way in the cable would have to be the same as the force going that way in the cable. You pretty quickly can see through that whatever force is in this cable here has got to be uniform throughout. In other words, whatever the force is here, it's got to be the same as the force here, same here, and so on and so forth like that, right? So in that case, if these are the same forces, then this force here must be the same as this force here, and whatever this weight is here, this would be half of it, this would be half of it, just equally distributed, right? So now we come up over here though, and we see the weirdity of this one is that, well, unlike that, now I've got 3 cables coming off this. The same thing applies though, it's continuity. So if you look at the continuity here, if the force here must be the same as the force here, 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 this has got to be the same force here, and that's going to be the same force here, you start seeing it's all going to be the same thing. So that means each one of these has to be 1/3. I mean, maybe it's easier to just write it this way. This has to be WB over 3, this has got to be WB over 3, and this one's got to be WB over 3. I think that might actually be an easier way to see it, and thank you for your questions that helped me to see that. Okay, so cool. So now if that's WB over 3, then that's got to be WB over 3. So does that, and so does that. Now I just have 2 of those WBs over 3, which leads me to that 2 WB over 3.
Okay.
Does that help?
Yeah.
Sweet. I appreciate it. This is a good question. Nate, I think I saw you had a question.
What is the pulley size?
Great question. So Nate's question, folks, is what if the pulley sizes, what if we did know they were different? What we would know there, Nate, is we would know the angle of this, right? So because of the dimensionality, we could figure out the angle of the cable. And even with that, this part is still true, right? What would be different though now is because of the angle, you could argue that you'd have a different, y force and x force there. But because we took that off the table, by saying we don't know that, so we're going to neglect that, that tiny little difference, that tiny little error that we might get, we just negate it. So, but to your question, if we did know those things, then we would be able to, instead of assuming they're all perfectly, vertical, we would know there is an angle on the one, we can figure out that angle. It's a good question. Yeah, fire away.
So it's sort of like elasticity of the belt. Assuming this is a rubber belt.
Oh man, what a great question that is. So, I'm gonna repeat it, so over here. So your question was, what if the belt was elastic, right? So in this particular case right here, we actually have the benefit, and we talked about this early in the course, that we assumed that there was no strain on any of the mechanical system. So remember the old, hey, if I sit on this table, it's gonna be smiling at us, right? We know that's reality. We know that there's gonna be mechanical strains in the cable, no matter what. But we have ignored them all along, right? Now, to your question, we get into a very different thing that goes way beyond statics here, where we look at the elasticity as being almost like a spring, in that if you extend a spring, you're building up kinetic energy, right? And there are analyses you can do that are based on energy analyses that extend the force analysis way beyond what we're doing right now, that can tell us more about how the mechanical element's going to behave. For our intents and purposes right now, we're like about 2 or 3 courses away from that. So I don't want to go deep into that, but I'll tell you, it becomes a thing in time. It becomes a thing in time. The good news for us, it ain't a thing right just yet. Good question though. Yeah, far away.
So if you have one of the cables at an angle on there, would the weight still be evenly distributed across the cables?
The tension would be, yeah, it would be. Because in that case, you'd still be, so what I was, and to Nate's question, so if we knew there was an angle, then you could say, well, there's a little X component, there's a little Y component, now when I add all the Ys together, it's gonna be slightly different. But it's so trivial, right? So we're not gonna worry about it. It's a good question. These are great questions, folks. I'm so glad you're asking these kinds of questions. This is good stuff. Anything else, anybody? Awesome. Okay. I see we're doing just fine on time. I think I'd like to just do is to put a little punctuation on this. I'd like to do just one more problem. I think this one's a fairly quick one. We won't eat up a ton of time on this one, but this is one of those where it's like I want you to think through, okay, if you had to do this, how would you do it? How would you assign your arrowheads and so on and so forth like that? So let me draw this thing up and we'll go from there. Going on the diagram for this one here, folks, let me read you the narrative. All right, the narrative goes like this: the 30-kilogram homogeneous cylinder of 400 millimeters diameter. So let's stop right there. So we are told that the diameter of this cylinder we see right here, the diameter is equal to 400 millimeters. So you can use millimeters, you can use meters, doesn't matter. I'll convert it over to meters. So 0.4 meters is the diameter, and we are told that the mass of this cylinder is 30 kilograms, so we know we're going to have to convert that over to, that's going to be some amount of newtons. It's not a weight yet, we got to do that part. So the 30 kilogram homogeneous cylinder, homogeneous is another word for uniform in this case here, homogeneous cylinder, 400 millimeters diameter, rests against the vertical and inclined surfaces as shown. So in other words, this is a cylinder that's wedged into some surfaces right here, so it's resting on the incline, it's resting up against the vertical, as you see right there. If the coefficient of static friction between the cylinder and the surfaces is 0.3. So once again, we have the same mu sub s as we had before, mu sub s here. Mu sub s is equal to 0.3. If the coefficient of static friction is 0.3, calculate the applied clockwise coupled m, or moment m, which would cause the cylinder to slip. We just simply want to know how much moment, how much torque would you have to apply to the cylinder here to get it to actually slip within this V-shaped thing that's holding it. Take a moment, just do a free body diagram of how would you draw the cylinder in this particular case right here, folks. And I'll get ahead of us just a little bit by pointing out that the force here, when we multiply this by 9.81, we're going to end up with 294.3 newtons. So let's just make sure we got that. So the weight here is 294.3 newtons. Take a moment and just figure out how would you do the free body on this one. Okay, folks, let's, I'm not sure where you're at in your process of doing it, but let's do some of the things that we know. We know there's gonna be this applied moment on there, and it was showed in the original diagram as a clockwise moment, so let's show it again as a clockwise moment there. We also know that this cylinder weighs 294.3 newtons, and because it's homogeneous, then we know that the centroid of the cylinder, as it would be with any circle, is right in its geometric center. So therefore, right down the middle here, I'm going to have this weight force of 294.3. As we continue looking at that, we realize, of course, that we would have a normal force, normal to this plane right here. We'd have a normal force, normal to this plane right here. So let's put those in place. I'm going to show a normal force here opposing. So remember, the cylinder wants to go this way, the normal force must oppose it. So normal force opposing that way. I'm going to call that one N. And the normal force I'm going to have down here, call it whatever you want to, but I'm going to show that as force, normal force I'll call force R in this case. So all right. It is worth noting too, folks, and that's just a little thing I want you to see, geometrically speaking, is the normal force here, which, by the way, worth noting, if this is a 30-degree angle right here, then that means that this angle here must also be 30 degrees. So I got 30 degrees right there. I am, by the way, going to use the standard XY axis system this time around. So let's keep that in mind. It's worth noting that these forces, the line of action of the normal forces, anything circular like this has to pass through the center. It's worth remembering that. That's going to be useful for us in a minute. And now the only thing we got to add to this free body diagram is our frictional forces. And we know that the frictional forces are going to exist along, collinear with the plane of contact. So I'm going to have a frictional force over here. I'm going to have a frictional force over here. And I need to include the arrowheads, contemplating the directionality here where these arrowheads are going to oppose the impending motion. So if you think about this, if you really did have a cylinder here and you're applying a torque that's trying to rotate this cylinder in a clockwise fashion here, that means this cylinder's edge is going to try to go clockwise, going this direction. So if it's going this direction, if that's the impending motion, then opposing the pending motion must have an arrowhead up here. In the same way, the cylinder is going to try to move this way, going as my finger's drawing right here. So if the impending motion is off that way, then the opposition of that would have the arrowhead going this way. And then lastly, we know that since our coefficient of static friction is 0.3, then we're going to have 0.3 N right there. And we're going to have 0.3 R right here. And lastly, folks, because of the angle here, we should see that this angle here has got to also be 30 degrees. In other words, since this is 30, this would also have to be 30 degrees on that angle. Now that right there is what the free body should look like. If you drew something that was, different than that, certainly make note as to, what needed to get cleaned up to better understand it. But now with that, folks, let's just go ahead and do the same old, same old. Let's do the sum of forces in the x direction, working from, I guess I want to go ahead and just get rid of this. I don't need this anymore, so I'm going to dump this. Let's sum forces in the x direction. We're going to have here, now, carefully, we're going to have minus n, noting again that this is positive x going that way, so minus n. There's going to be an x component of this one that's going to be tending towards positive. That's going to be 0.3 r times, in this case, the cosine of 30. So plus 0.3 r cosine 30. And then this r force here is also going to have an x component that's tending towards positive x. This one's going to be r times, in this case, the sine of 30. And again, tending towards positive, so plus r sine 30. Worth noting that this one's purely y-directional, this is purely y-directional, so we need to worry about those. And of course, the moment is not going to show up in a force equation. So that equation by itself is going to be equal to 0. Let's call this one equation 1. We'll come back to it shortly. Now, let's sum up our forces in the y direction. call this one equation 2, by the way. So now in our y direction, working from over on the far right side, I got 0.3n, purely y directional, pointing in the positive direction. I've got minus 294.3, purely y directional. This one here is tending towards negative y, so it's going to be minus 0.3r times, in this case, the sine of 30. And the y component of this one is going to be plus, it's tending towards positive y, so plus r times the cosine of 30. And that takes care of all the y forces, so that one's going to be equal to 0. So as it stands right now, I've actually got two equations with two unknowns. I can actually solve for n and r in both of these equations, but it doesn't tell me anything at all about the moment, right? We were asked to figure out what the moment's going to be that's going to cause slippage, so that leads us to an equation 3. Where equation 3 in this case, we're going to sum moments, and as we all know, we can sum moments literally anywhere we want to. But think about this, folks. The most logical place to sum the moment is going to be right through the middle of the center of the circular thing. In fact, let's just give that a label. Let's call that point O for origin. So if I sum my moments now about O, remembering as always that counterclockwise is positive. So we start things off with moment itself, the thing we're looking for, which is drawn as clockwise, so therefore negative. So I've got minus m. And then very importantly, the 294.3 goes right through the moment center. But so does the normal force here. The line of action of r passes right through the moment center, and the line of action of n passes right through the moment center. So they're not in play. So nothing due to this, nothing due to that, nothing due to that, but I got that 0.3n right there. And we see the way that that's drawn with the moment center over here at point O, we see that the way that that's drawn, that would cause a counterclockwise about point O, so it's going to be positive, so plus 0.3n times the moment arm. Now folks will recall that we were told from the narrative of the story of the problem that the diameter here was 0.4, right? The moment arm is the distance from the center over to the line of action of that, which is going to be the radius of this, so half of our 0.4. So that means that our moment arm is going to be 0.2 in this case. And then we look down here at the 0.3r, that too, with respect to the moment center here, that also would be causing a counterclockwise rotation, so we're adding that one. So plus 0.3r times its moment arm, which is 0.2, because of the radius again, and that takes care of it. So now we can set that equal to 0. Now we have three equations, three unknowns. Let's do a little bit of work right here, folks. From equation 1, if we solve for n, we're going to find that n is going to be equal to, and we can see it right there, n is going to be equal to 0.3r cosine 30 plus r sine 30. And when we add all that stuff up, folks, we're going to find that n is going to be equal to 0.76r. So from that, if we substitute this into equation 3, in other words, I'm going to now substitute n is equal to 0.76r. Now I'm going to have m as purely a function of r. So by the time I get done with that, I'm going to have m is equal to, by the way, 0.3 times 0.2 gives us 0.06. So 0.06 times n, which is 0.76r, plus another r. So let's just add another r to that. In other words, I'm taking care of this term here as well. So when all is said and done here, folks, I'm going to have that being equal to 0.06 times 1.76 times r. And I'm just down now to figuring out what r is, and I can do that from equation 1. So now if we plug into, equation 2. I took care of 1 and 2. So now from 2, I'm going to have the following. I'm going to have 0.3 times n, but we've already asserted that that's 0.76 times r, minus 294.3 minus 0.3 times 0.5 for the sine times r. And I can't see it, there's a plus, yeah, that's a plus. So plus r times the cosine of 30, which is 0.866. And that's all equal to 0, which means that 294.3 is going to slide over the other side equal sign. I now have an equation that is entirely in r. And folks, when we solve this equation for r, we're going to end up with r then is going to end up being 311.75, so 311.75 newtons. If I substitute that in right here, I'm going to find that n ends up being equal to, so about 3/4 of that, or 0.76 times 311 point whatever that is, 75. That ends up being 236.9 newtons. And now that I know what that is, I can substitute in right, well actually since I already had r, I could solve for the moment here. All this combined gives me the moment that I was looking for of being 32.9 Newton meters, and the problem is solved. Just like that. And again, I know I'm beating a dead horse. I hate beating dead horses, but I have to. When I say, yeah, the problem, if you just look at problems, the same old stuff. We're being asked to figure out a bunch of different things. In this case, well, how much torque would I need to have? But the methodology that got us there just didn't change. It was a free body diagram. In this case, now we're applying friction. After that, the equations of equilibrium. Do you notice the equations of equilibrium just never change, right? They're the same old, same old. The equations of equilibrium, solve them, problem solved, done. There we have it. And that takes care of chapter 6, folks. That's as far as I want to go with chapter 6. We've seen now a number of examples of how to apply friction. My strong encouragement is to make sure you work a couple of those. There's a couple of them available, see on Blackboard in the chapter 6 set that I set up for you early in the semester. Work those, make sure you're okay with them, and we're going to be fine. Does anybody have any questions about that before we leave it? Okay, folks. Thanks. I'll see you all on Thursday. For those of you that want to chat with me, I'm going to be here. Like I said, I got till noon. They got to rock.